Good morning. So, carry on from where we left off in the last lecture. We were looking at radiation heat transfer and some terminology in radiation heat transfer. And we looked at the definition of intensity of emitted radiation in the last class. And we did one example based on that. So, let's just take it further. And now let's look at radiation that is incident on a surface. So, we will define I lambda I, which is lambda function of lambda theta and phi, which means it's a function of wavelength and a function of direction, to be the rate of radiant energy that is now incident. So remember that, as I said, I was using some terminology in the last class. I had I lambda comma E, where meant emitted radiation. Now I have I lambda I, where I basically means incident radiation. So we have rate of radiant energy, which is of wavelength lambda, which is incident from the theta phi direction per unit area the intercepting surface. So on the surface on which it is falling. But this area is not just any area, it is also the projected area. So that is area along the normal, okay, or area perpendicular to the normal, the way you want to say it. So intercepting surface, which is normal to this direction. And I'll show you by a simple example or a simple sketch. Per unit solid angle, about this direction, and per unit wavelength interval, which is d lambda, about lambda, of course. So we define incident radiation to be, it's called as irradiation. So when I say irradiation, I would be saying that this is irradiation, okay, surface. So say we have a surface, let's say, which is aligned in a certain way, and its normal vector goes in a certain direction. The surface has, let's say, infinitesimal area dA1, and there is radiation coming in from a certain direction. So say the radiation is reaching this surface maybe in this direction. So what I'm saying is that for characterizing this radiation, we need to take the area which is the projected area along this direction. So if I say that this surface or the normal vector makes an angle theta with the incident radiation, then what it means is this angle is also theta, and so the projected area is again dA1 cosine theta. So based on that, we can also define what would be spectral irradiation. Special symbol for irradiation, by the way, we use the symbol G, okay, for when we characterize irradiation. So we can write spectral irradiation to be G with a subscript lambda. So spectral irradiation is essentially sum of radiation received by a surface from all directions. So this will be 0 to 2 pi, 0 to pi by 2 of I lambda theta phi cosine theta sine theta d theta d phi. So it's spectral. So the spectral the word itself means that the wavelength dependence is still there. Okay. Similarly, I can also write the total irradiation. So total irradiation will mean we're calculating the total radiation received from in terms of all wavelengths. So all wavelengths have been accounted for. We will use a symbol G for that. So G would be written as integral 0 to infinity of G lambda lambda d lambda, and we can write this as integral 0 to infinity integral 0 to 2 pi 0 to pi by 2 of I lambda I times cosine theta sine theta d phi d lambda. So a special case can be made if we say that the irradiation is diffuse. So if we say that the irradiation received by a surface is diffuse, and you'll use this word very often now. In fact, most of the first analysis that we do in the first course is based on diffuse irradiation or diffuse surfaces, and I'll talk about that. But what diffuse would mean is that we have the irradiation now being independent of, so I lambda I is independent of direction. So I lambda I is only a function of, sorry, is only a function of wavelength. The direction dependence is now taken away. So then you can write, for this special case, G lambda would just be pi times I lambda I of lambda, and that is easy to obtain because if I say that I lambda I is in this equation is independent of theta comma phi, so it goes out, and then you can easily integrate the whatever is in the integrand, which is only a function of theta, and that is quite easy. So we should get G lambda I to be pi times I lambda I, and G, which is the total irradiation, would just be pi times the total radiation intensity, which is essentially sum over all lambdas. So these are certain common things that we will use in terms of irradiation on a surface. But now as we move forward, there would be some additional complications. So we have sort of looked at a surface emitting radiation. We have looked at surface receiving radiation or radiation being incident on a surface. Now we look at another aspect, that a surface not only emit, but it can also reflect the incident radiation. So say we have maybe a surface on which there is some irradiation. The surface emits because of its finite temperature, so there is emission. But the surface also reflects part of this irradiation. So this is the reflected irradiation. So we have another quantity which combines these two, because if you are thinking of the surface, the surface is doing both. It is also reflecting, it's also emitting. So we look at, so if you're looking at radiation received from a surface, or what a surface is actually throwing out in terms of radiation, it should be the combination of these two quantities, both the reflected and emission radiations. So we call this combined radiation as radiosity, and radiosity is typically given by the symbol J. So we will talk about spectral, let's say, radiosity, which will be J lambda, which is as a function of lambda, of course, and its units are again watt per meter square per micron, or per micrometer if you want to be more strict. But this accounts for all the radiant energy leaving a surface. So J lambda could be written as the directional sum, so 0 to 2 pi, 0 to pi by 2 of all, let's say, radiation emitted plus reflected. So we can say it's the intensity of emitted plus reflected radiation as a function of lambda theta phi cosine theta sine theta d theta d phi. By the way, I don't mean that I lambda e plus r is just I lambda e plus I lambda r. I'm not saying that. Okay, it is not that simple. But this is the total radiation that you should. I mean, this is a new quantity, a new intensity, which accounts for both emitted and reflected radiations. So this is the spectral. So I can call this as spectral radiosity. We can also define the total radiosity, which would be A, which I can write as integral 0 to infinity of j lambda d lambda. And that, again, we can put the, I mean, this is one way of writing it. Otherwise, you can always combine the integrals, and so you can write it as a triple integral, which is fine. Now, if a surface is both a diffuse emitter and a diffuse reflector, so if a surface is diffuse emitter, a diffuse emitter would be one in which the emission is independent of direction, and I said a diffuse reflector, which would mean that the reflected radiation is also independent of direction. Then we again have that this I lambda, the intensity of radiation, which is typically we write in terms of the directional dependence, is only a function of wavelength. So remember, I use words here. One is diffuse emitter, so it has to be both. Only then what I'm going to write is possible. Okay, so and is important. If it's a diffuse emitter and diffuse reflector, then we can write I lambda e plus r to be only a function of lambda. And in that case, the radiosity, so I can say J lambda, spectral radiosity, would again be pi times the intensity, and total radiosity J would be pi times the total intensity. So we have now looked at irradiation and total radiation leaving a surface. So now let's look at some characteristics of a real surface. Okay, how do we define a real surface? So I'm going to look at surface emission. And I'm going to look at emission from a surface, from a real surface. So we're looking at real surfaces. But we will define real surfaces in terms of an ideal surface. So typically a real surface will be one in which if I plot, let's say the spectral emission characteristics, so let's say E lambda, the spectral distribution versus lambda, what we will see is some kind of a variation with lambda, some irregular variation. And if I also plot, let's say E, or rather I should not plot, I'm not saying E, but rather the intensity, sorry. So if I look at the surface, okay, which has a normal vector somewhere, let's say. So if I plot how a real surface emits in different directions, okay, we will have maybe a distribution which would look like something like this. So where I'm measuring angle theta in this direction. So that is the polar angle. So we will have, use a different color for this. So we will have intensities being dependent on the angle theta. So this is, you're plotting I lambda E. So real surface is one in which the emission, as I said, spectral emission and the directional emission are both, they differ in terms of wavelength, they differ in terms of direction along which you are emitting. So this emission actually depends on a number of factors, and this is what I want to describe today. So the amount of radiation that the surface emits depends on lambda. I'm not concerned about lambda only. It also depends on a few factors. Depends on factors such as the temperature. The emission also depends on the material of the body. As part of the reading assignments that I have given at the beginning of the course, I listed a bunch of things that you have to read. So if you look at the radiation chapter, you will see that conductors and non-conductors, or even metallic surfaces and maybe glassy surfaces, they actually have different materials and they have different radiative properties. So the material of the body itself dictates the amount of radiation that a surface emits. And the third thing on which this matters is the condition of the surface. By condition of the surface, I mean whether the surface is rough or whether the surface is smooth, like mirror-like finish. So these are the three factors on which radiation emitted by a surface will depend on, or will be dependent on. Further, even if I look at surface temperature, two bodies which are at the same surface temperature may emit different amount of radiations. So it is not just that the temperature is the same, so two bodies will emit the same radiation. So as you can see, the material, as I said, the material also matters. So two bodies at the same temperature will not be expected to emit the same radiation. Problem is further complicated because we cannot be measuring all these, or it's quite a difficult task to keep measuring these spectral, distributions or distributions for any surface at a given wavelength or for a range of wavelengths. Not an easy process. So what is typically done is we always look at emission with reference to some kind of an ideal body, or we look at what is the maximum amount of radiation that a body can emit. So the question of maximum amount of emission that a body can emit leads us to the concept of a black body, or an idealized body, if you want to say. Black body is a more common term that is used. So an idealized body or a black body is one which is actually a perfect emitter and also perfect absorber of radiation. By a perfect emitter, I mean that due to its inherent temperature, it will be emitting the maximum possible radiation for any body that is at the same temperature, or compared to any body at the same temperature. Perfect absorber would mean that any radiation that is incident on this surface, which is any radiation, completely absorbed. So we talk about perfect emitter and perfect absorber in that sense. So please remember a black body, as I'm saying, so a black body is one absorb all incident radiation. So that would mean that any wavelength, it is not being said of a certain wavelength only. For all wavelengths, it will absorb all incident radiation. And second thing is that this black body is one which emits radiation in all directions, or rather, I should say, emit radiation uniformly in all directions. Uniformly in all directions, which basically means since it's emitting uniformly, it is a diffuse emitter. Which is it's in the emission is independent of direction. So if I go back to my sketch that I had done, and I'm pardon me for just scrolling up now. So if I go back to this, we are talking of a black body which would have maybe the maximum saying has the maximum possible emission. So that would be maybe this surface or this curve, which we see what it looks like. So this is the emission from a black. Okay, and this was the real surface. Yellow was the real. I should have mentioned. And similarly, because a black body is one which emits uniformly in all directions. So if I take this as the center, then a black body is one which would have maximum emission but also uniform. So it will have uniform intensities in all directions. Okay, so theta is this, and so this is E, not E, sorry, I lambda B, which is only a function of lambda. There's no theta dependence now. It's the same everywhere. So using this benchmark, we can then define certain properties of these surfaces. Now, the last thing, before I define any property, the last thing I want to say about a black body is that there's a notion that any surface that is black is a black body, or whatever appears black to the human eye is a black body. Now, that is not correct. Simple reason that the emission that what you're seeing, basically what you're perceiving as a black surface, is actually in a very narrow spectrum. The spectrum that corresponds to visible radiation, which is about 0.4 to 0.7 microns only, or 0.75 microns. So it's a very narrow band of the entire spectrum. And so something that appears black in that spectrum may not be black in the other wavelengths that our human eye cannot perceive, or we don't have the sensory perception to be able to make out uh, whether it's actually really black or not. So just because the surface is black, judgments should not be passed on whether the surface is black or not. Okay, and again, I'm saying black, I'm not saying in terms of visual, but I'm saying in terms of black body, that if a surface is black, it doesn't mean it's a black body. Please remember that. Okay, it appears black, but it need not be a black body, that it need not be a perfect emitter. Now, no surface in reality is a black body. There is no perfect emitter. It's a concept that we develop to define some or to make it easier in terms of mathematical treatment. And I'm sure you also did these maybe radiation type problems, looking at or using the Stefan-Boltzmann law in JE, or at least that time. So we tend to make certain assumptions, but no surface is a black body. The closest we come to a black body is if, let's say, we have a sort of a cavity. Okay, let's say we have a cavity which is, I don't know, some regular shape, I don't care, which has a small opening. Okay, so this is a cavity which is a constant. By the way, the cavity is at some constant temperature. The entire cavity surface is at a constant temperature. And say we have some incident radiation coming through this cavity, through this aperture. Okay, so let's say we have some radiation coming, which is I should say lambda I coming in through this aperture. So this cavity, which has a small aperture, can actually be considered to behave like a black body. And let me put my arguments for that. Okay, so if you look at this incident radiation, this will actually have, when it falls or when it hits a inside part of the cavity, it will actually start reflecting. Okay, it will have reflections which maybe will take it to different parts of the cavity. Something like that. So with each reflection that this radiation experiences, some part of it will actually get absorbed. We'll talk about absorption later, but for now you can assume that it does not completely, radiation never completely reflects. There is always a part that is absorbed on the surface. So some part gets absorbed, and so these multiple reflections uh, enable this radiation to be completely absorbed before it re-emerges from the aperture. The first point that I'm making is that multiple reflections of incident radiation can lead to complete absorption of the radiation, of this incident radiation. So before it can escape, this incident radiation can be completely absorbed, and so we can say that at least it's a perfect absorber of radiation. This cavity is a perfect absorber of radiation. The second concept in this, whether it's a perfect emitter or not, is that if you look at this cavity now, which I said is a cavity at a constant temperature, surface at a constant temperature, in itself when it emits, and let's say as an observer you are sitting out here, right? I can draw maybe, let's say now you are sitting here, you're watching this from here, or you have a sensor which is see what radiation emerges from this aperture. So when this cavity is emits because of its finite temperature, the emission itself will actually undergo many reflections within the cavity. So these, and each point, by the way, is reflecting. Keep remembering this. Each point on this cavity is reflecting, or is not reflecting, rather is emitting radiation. So whatever emerges from this aperture would actually have no directional sense because it would have undergone so many reflections. So radiation that is emitted by this cavity will have a diffuse nature, that it would have lost its directional sense by the time it emerges. So we can now say that this cavity is also, in that sense, it's actually also a perfect emitter because it is emitting without, or it's emitting diffuse radiation. Finally, if I look at a surface which I placed inside, say hypothetically I had the luxury, and maybe I could place a surface inside this cavity, a small surface which does not interfere with the radiation. Then because the radiation that is emerging from the aperture should have the same nature as the radiation inside the cavity, then it means that this surface should also be seeing a radiation or an irradiation which would be diffuse. So I'm trying to draw this here, that it is uniform in all directions. So the radiation incident on this surface, which is G lambda, spectral radiation, should also be, or should resemble, the radiation corresponding to a black body, uh, spectral radiation. So if we if we take these aspects of a cavity, and again, this is a concept that we will use very commonly for many problems which are, where we will assume that the surroundings, you can imagine now this is that, you have a surface which is in a surrounding space, and the surroundings are much larger as compared to the body. So the surroundings are very far away, and so they can be assumed to be, diffuse emitters. So such a cavity will be assumed to be a, sort of like a representation of a black body. And so typically in such problems, we then need to calculate what is this distribution, E lambda B, which I also have drawn in the earlier sketch, which I also had here, right? So what is this distribution is something that now we come to address. So this distribution, or the spectral distribution, is what was given by the work of what was derived by Planck. So the spectral distribution of black body, it begins with the concept of, again, defining the intensity, the spectral intensity I lambda B, which is a function of lambda in temperature. So this is given by, which was actually derived by Planck, to be 2h c naught square by lambda to the power 5 exponential of h c naught by lambda kt minus 1, where h is the Planck's constant, which is 6.63 or 6.625 something, 10 to power minus 34. I think joule second is the correct units. K is the Boltzmann's constant, which is 1.38, 10 to the power minus 23 joule per Kelvin. T is of course the temperature, absolute temperature in Kelvin. Lambda is the wavelength. C naught is the speed of light in vacuum. So this is 2.998, 10 to the power 8 meter per second. So the spectral emission of a black surface would be given by this law. Now, because I was saying that the black body is one which emits the maximum amount of radiation, and it also is a diffuse emitter, it so follows that from one of the earlier or from the last lecture, where we looked at for a diffuse emitter, we derived this thing that E lambda B, or rather E lambda I should say, but I'm just putting subscript B to define a black body now. E lambda B, which is a function of lambda comma T, for a diffuse emitter would just be pi times the intensity of radiation at the same lambda in temperature, which I defined as spectral spectral emissive power. I'm dropping the word hemispherical because it's understood that it's direction independent. So that is the reason we get a pi on the right hand side. So the spectral emissive power for a black body is E lambda B, which is pi times I lambda B. And so if you plug in this expression, we get now h c naught square. 2 into h c naught square is a constant, times pi is also a constant. So I'm going to write this as C1 by lambda to the power 5 times exponential h c naught by kt, h c naught by k rather, is also a constant. So we'll write this as C2 by lambda t minus 1. So E lambda B actually has the spectral emissive power from a black body has a very specific form, which is what was actually known as the Planck's distribution. So the Planck's distribution basically dictates or defines this maximum emissive power from a black body at a given wavelength. Of course, now we'll look into another aspect of it. So here C1, this constant C1 is 3.742 10 to power 8, 10 to power 8 watt times micron 4 by meter square, and C2 will be 1.439 10 to power 4 micron Kelvin. So let's just discuss what this plot or what this distribution looks like. So I've drawn something, I've drawn something here. So I want to now just show you what it, and I know you have seen this actually. If not in JE, at least I don't know whether you did, you must have done a first year course on physics. So we were taught this distribution when you were doing what art at our time, this course was called modern physics. So we were actually asked to even derive this distribution using the, using some basic principles. So I don't know, maybe you also would have done that. But anyway, let me just try and bring the distribution here. Yeah. Okay. So this is what the Planck's distribution would look like. So we have spectral emissive power on the y-axis, as you can see, spectral emissive power on the y-axis, wavelength and meter on the x-axis. Okay. So for different temperatures, you get different emission curves. Now there are some things that we have to take note of. First of all, if you look at the y-axis, which is the spectral emissive power, so the magnitude, first thing, more importantly, remember that this plot is actually on a log scale. So the x-axis is on a log scale, the y-axis is also on log scale. It's not a linear scale. So it may appear, that, oh, it's a simple curve, but it's actually on log scale. So you have to interpret this very carefully. The second part is that if you look at the emission because of, or the temperature dependence of emission, so the maximum value or the magnitude of emission increases as the temperature increases. So we are going from 50 Kelvin to 5800 Kelvin. 5800 Kelvin because it is a very special emission which is from the sun, so solar emission. So as we go higher in temperature, the magnitude of the emission is actually increasing. So we have something like 10 to power 8 here. At 50 Kelvin, we have about 10 raised to minus 3 or minus, between minus 3 and minus 2 watt per meter square microns. So that is part one. Typically, we, in most calculations in heat transfer, we'll assume sun to be a black body, which is a black body approximated at about 5800 Kelvin. So if we assume, if we take it as a black body, we see that visible spectrum, which is this grayed out portion, or I should put the other way around, that the maximum irradiation which we are receiving from the sun actually is in the visible part, is in the visible spectrum part, which is about 0.4 to about 0.75 microns. So most of the radiation that we are receiving is visible in that, is in the visible part of the spectrum from the sun. The third thing that you would have done in during your JE time, I'm assuming, I don't know how much JE has changed now, but during the JE time, you would have actually heard of this law, which says that the maximum radiation times temperature is a constant. So we can actually very quickly see why that is the case. First of all, this line, this dotted line, actually shows the locus of these curves, which is lambda max times t is a constant. Okay, so the locus of these points is actually what is given by the dotted line. So to obtain the wavelength at which maximum radiation or at which maximum emission occurs, we just use this radiation or this distribution and differentiate that with respect to lambda. So we say that d e lambda b d lambda is 0. If you do this differentiation, then what you get is lambda max times t to be a constant, which is 2897.8 micrometer Kelvin, which is what is called as the Wien's displacement law. I think if I remember in the book by Inkrupera, this is a problem that you can work out. You can differentiate, and although it's not very hard because the function has a lambda to the power 5 dependents, but still you can differentiate. Or the other way around to look at it is that if you look at this distribution, to maximize E, you need to minimize the denominator. So you can sort of minimize, so differentiate this and say that under what conditions is this minimum. So that can also be done. But if you do this, you should actually be able to obtain this relationship. So the Wien's displacement law basically is saying that at a given temperature, you have a maximum wavelength at which most of the radiation is concentrated. In the case of sun, if I look at this equation now, assuming let's say this is 2897, can be roughly approximated to be 2900 micrometer Kelvin for now. As engineers, we're engineers, we understand we can make some approximations. So if I take this as 2900 micrometer Kelvin and the temperature is 5800 Kelvin, then clearly lambda max is roughly around 0.5 microns. So that is where this point is, 0.5 mics. Okay, this point. This here is about 0.5 microns. So it's right in the middle of the visible spectrum. Now, the total emissive power of a black body, which can be obtained by doing a spectral integration. So I can say EB would be integral 0 to infinity, so integration over all wavelengths of the spectral emissive power, E lambda B d lambda at a given temperature. So this would be integral 0 to infinity of C1 by lambda to the power 5 exponential C2 lambda t minus 1 d lambda. So this integral actually is also doable. If you're not familiar with Riemann functions, you may think, what is this how do you do this? But it is doable, and this actually then comes out to be sigma times t to the power 4. If you can work out, it would be great. I think I would encourage you to try and do this, but if you're not, let's not worry about it. But the point is that the total emissive power of a black body comes out to be sigma t to the power 4 because of this dependence, and this is what is called as a Stefan-Boltzmann law. So EB equal to sigma t to the power 4 is known as a Stefan-Boltzmann law. The reason it's called Stefan-Boltzmann's law is because even though Stefan was one of the first ones to derive it, Boltzmann actually verified it a few years later. So Stefan-Boltzmann law, sigma being the Stefan-Boltzmann constant, which is 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. So what we've been using very casually, and even I have done, actually my derivations are also very casually done. I'm not going into the detailed mathematics of it because that will take forever to, few lectures. I should not say forever, but a few lectures to be able to derive. But broadly, this is how we get to the Stefan-Boltzmann law. So now we have sort of covered the idealized surface. The last thing I want to cover about these ideal surfaces, which will actually help us in our calculations, is one concept which is related to band emission from a black body. So we can use these quantities that we've defined so far to quantify. Let's say if I had maybe some emission from a black body, say E lambda B versus lambda, and I've said that this is a curve of maybe this type. And the objective that I have is to quantify how much radiation is between a band, let's say from 0 to lambda. So how much of the total emission is between some wavelength range, let's say 0 to lambda. So we define a fraction of radiation in this band. This is what is I'm going to call it as band interval, or emission in a band interval. So we define that sort of using a quantity which is f, which is a fraction. So let's say 0 to lambda. That would say that we're quantifying at a given temperature how much radiation from a black body is between wavelength 0 to lambda. We can write this as the integral of 0 to lambda, or from 0 to lambda, of E lambda b d lambda versus the total radiation under this spectrum. Now it's easy to see that integral E lambda b d lambda from 0 to infinity would be sigma t to the power 4, which is what we have just now done, right? We wrote 0 to infinity E lambda b d lambda is sigma t to the power 4. So this becomes sigma t to the power 4. So I can write this integral in a slightly different way. I can say that sigma t to the power 4 would be in the denominator, which I'm going to pull out and write this as 0 to lambda. Let me also include, or let's forget about it. So E lambda b sigma, let's say t to the power 5 d lambda t, because temperature is constant. So I can write this as, the integral as integral e lambda b by sigma t to the power 5. Sigma t to the power 4 came from the denominator, and times d lambda t. Now the reason for doing this is that if I look at E lambda distribution, E lambda b by sigma t to the power 5. So if we look at E lambda b by sigma t to the power 5, what we will have would be C1. Remember, there was a lambda to the power 5 in the denominator, so we'll now have sigma lambda t to the power 5 times exponential C2 lambda t minus 1. So now I can see that this distribution actually has a lambda t to the power 5 and a lambda t here. So this distribution is sort of a function of lambda t only. So it's a function of the product lambda t. And so the purpose of writing a d lambda t here is that now we can define a dummy variable sort of as a lambda t, okay, as a dummy variable, and then do the integration if need be. But these actually integrals are already computed. And so what we will see, as I will show you now in a second, in your book, these integrals 0 or this fraction band emissions are written in terms of a function of lambda t. So lambda is basically the wavelength to which you are trying to quantify this radiation. So what you will see in your book, let me also bring this now here, because we will use this to do a lot of calculations going forward. What you will see in your book is a table of this type. So you will see that, so for a value of lambda t, okay, if you at a given temperature, let's say you want to calculate till a certain wavelength how much of emission is within that band. So that number f0 lambda is actually given as a function of lambda t now. So if you choose some, let's say, wavelength at a given temperature, you can actually read up the value of f from this sheet or from this table. And typically what I do is, if I have a data in the middle of any two data entries, I just use linear interpolation. We don't need to worry about getting very precise with these calculations. So these kinds of data tables are there. The integrand is also, there are also some additional data which you will see how it will be used, because again these are values which typically go in the integrand. And similarly, this rightmost column is actually about at the current lambda t versus what is the intensity at the maximum. So clearly, when you have Wien's displacement law where lambda t becomes 2898, this is the Wien's displacement law value. So there the intensity is actually has a ratio of 1. So the intensity at that point, or at that lambda t, versus the maximum intensity is what is given. Okay, so this is listed there as 1, and it basically increases and then it decreases. So that is what this column indicates. But we would be more concerned with, as I said, with this column. Okay, this will be of our interest. So there are two parts to this table. I've only included one. There is another part which basically goes beyond 9,000 micrometer Kelvin to infinity, because remember the band will go to large values of lambda. Okay, so this table is there. So you will have to use this table to do these kinds of calculations for band emissions. Now let me also put one more question here. So we said from 0 to lambda we can calculate the amount of radiation prescribed in that band. Say I was interested more in maybe emission between maybe two wavelengths. Let's say lambda 1 and lambda 2. We have lambda 1 here, lambda 2 here. And I'm more interested in knowing how much emission is within this band between lambda 1 and lambda 2. So this is also can be done using the same idea that we have. We can use f values here, because what I want to now calculate is f, let's say lambda 1 to lambda 2, which is of course not given directly at a given temperature. So this can be written as integral. So you see that it's the area under the curve that we are calculating. So the spectral curve, I'm just looking at area under the curve. So I can calculate the area under the curve up until lambda 2 and subtract the area under the curve until lambda 1. So we can say this is 0 to lambda 2, right? E lambda b d lambda minus 0 to lambda 1 E lambda b d lambda, that is the area, versus of course by EB, which is sigma t to the power 4. And so this is going to be the same as f value from 0 to lambda 2 minus f value of 0 to lambda 1. So if you're given two wavelengths, you can easily calculate at a given temperature, you can calculate what would be the lambda t values at those two wavelengths, and then subtract the f values to obtain what is a emission within a narrow band or within a band of radiation. Okay, so having done this black body behavior in such great detail, now let me define some properties of the real surface or emission from a real surface. So let's look at a real surface now. So to define or to characterize a real surface behavior, we will use different quantities. So we'll first go with emissivity. So we can define spectral, directional, emissivity of a real surface, which I'm going to write as epsilon lambda theta, which is a function of course, direction and temperature. So this becomes the ratio of the radiation emitted by a surface, a real surface, at a given wavelength, in a given direction, at a given temperature, versus what a black body will emit at the same wavelength and at the same temperature. So this radiation intensities, the ratio of the radiation intensities is what will define the spectral directional emissivity. And the sketch that I had drawn in the early part, I mean a few, maybe about 30 minutes back in this class, where I had shown the directional values. So basically what we were looking at was the ratio of the directional emissivity, or the directional intensity versus the black body intensity. So you can sort of say that if I take the ratio of those two quantities, we would have got this value of epsilon lambda theta, or the spectral directional emissivity. There is one more emissivity. If you do an average over all wavelengths, you get what is called as a total directional emissivity. So in a given direction, it sort of signifies an average over all, or I should say sum over all wavelengths. So we can define this as epsilon theta. So in the direction theta phi t would just be the emission in that direction versus the black body radiation, or black body radiation intensity. But this is rarely used. We will not do any problems, at least, which have total directional emissivity. And as engineers, we try and always average over directions. We don't average over wavelengths, but we try and work with average over directions. So this is very rarely used. So as I said, in most engineering systems, we will work with directional average quantities. So we can look at the first directional average quantity, which is the spectral hemispherical emissivity. Now, because I'm saying hemispherical, remember this means that this is averaged over all possible directions. So we define spectral hemispherical emissivity as epsilon lambda at a given temperature to be the ratio of the spectral emissive power at a given lambda at a given temperature versus the emissive power from a black body at the same lambda at the same temperature. So this can be written as integral 0 to 2 pi. Remember, it's hemispherical, so I'm just going to write this in terms of hemispherical quantities. So intensity of radiation, which is lambda theta phi t, cosine theta, sine theta, d phi, versus the radiation from a black body, which would be I lambda b, which is only a function of lambda comma t, cosine theta, sine theta, d phi. So the denominator has a very special aspect here, or special nature, because we said that a black body is a diffuse emitter, so its radiation is independent of direction. So I lambda b is independent of direction, which means that I can take it out of this integral from the denominator and put it into the numerator. So if I put it into the numerator now, if I take I lambda b out, put it into the numerator, because the integration is with respect to direction, not with respect to wavelength, then I can see that I lambda e by I lambda b would actually become the spectral directional emissivity. Can you see this? So this will be the spectral directional emissivity. So I can write this as, the next step would be to write this as integral 0 to 2 pi 0 to pi by 2 of epsilon lambda theta phi t, cosine theta, sine theta, d phi, and the denominator would just be 0 to 2 pi 0 to pi by 2 cosine theta, sine theta, d phi. The denominator is quite easy to compute. This will actually come out to be pi. The integral will be pi, which I think we did in the last class, if I remember correctly. We said integral sine theta d phi was 2 pi. When you put a cosine theta there, you get integral as pi. And so that becomes pi. And frequently it is also assumed that the azimuthal dependence of radiation is sort of, or rather the radiation emission is sort of assumed to be independent of the azimuthal radiation. We assume that if the angle phi, which is the angle in the plane, that dependence is not there. It's only with the polar angle, which is theta. So if you take that, then integral d phi, if I say that epsilon lambda theta is independent of phi, then this becomes just d phi just becomes integral d phi becomes just 2 pi. So pi and pi cancels, and so what you will get typically is integral 0 to 2, or rather 2 times 0 to pi by 2 epsilon lambda theta, which is just a function of lambda theta t, cosine theta, sine theta, d theta. So this is if we assume epsilon lambda theta to be independent of the azimuthal angle. Okay, so we've defined the spectral hemispherical emissivity. Now we can define the total emissivity, which is the total hemispherical emissivity. So this will be epsilon as a function of temperature only, and which would be of the total emissive power from a surface, a real surface, versus the total emissive power from a black body at the same temperature. So this then becomes integral 0 to infinity epsilon lambda t e lambda b lambda t d lambda by the total emission from a black body. So these are characteristics of a black body. Okay. Anyway, so I'll stop here now.